In this lesson, we're going to learn about some of the theorems about polynomials that help us solve polynomial equations. Okay, so the first one we're going to talk about is the remainder theorem. And so if we were to go ahead and take this function and divide it by x plus 4, let's see what we would get. I'm going to use synthetic division. So you can see what I would get is x squared minus 3x plus 8, and then 9 is my remainder out of x plus 4. Okay, so now I'm going to go ahead and I'm going to evaluate f of negative 4. And let's see what we get. So when I evaluate f of negative 4, I get 9. And guess what? It's the same as my remainder. Coincidence? I think not. That's because the remainder theorem says, so the remainder theorem says that if a polynomial function f of x is divided by a linear zero, or a linear factor, then the remainder is the same as evaluating the zero of that factor into the function. And the remainder theorem leads us to this important theorem about polynomials, called the factor theorem. It says that if you have a polynomial function, f of x, and x minus c is a linear factor, then when we evaluate c in the function, we should get a remainder of 0, because f of c would be equal to 0 because it's a 0. So let's test this. Okay, so I have x cubed minus 31x plus 30. So instead of using division, I'm going to go ahead and I'm going to do f of the 0 of the linear factor. So I'm going to first try negative 1. So that gives me negative 1 cubed minus 31 times negative 1 plus 30, which gives me negative 1 plus 31 plus 30, which guess what? It does not make 0. Which guess what? Does not make 0. So since this is not equal to 0, it is not a linear factor. Let's say the same thing with f of 5 and f of negative 6. You could do those on your own. So how'd you do? So really and truly, it's not a big deal what it actually is equal to if we're trying to figure out if it's a factor. We just need to know, does it equal 0 or does it not equal 0? In this case, x minus 5 does make a 0. X plus 6 does not. So that means that when I take this and I divide it by x minus 5, I would get a remainder of 0 because x minus 5 is a factor. So now let's go ahead and we're going to use the factor theorem, and we're going to go ahead and we're going to factor a polynomial completely. So using the factor theorem, I want to go ahead and I want to factor this entire polynomial. Now I know I can actually factor it, but let's pretend it's not factorable for a moment. Okay, so first I'm going to go ahead and test to see if it is a factor. So if it is a factor, then when I evaluate it with the 0 of x plus 3, I should get 0. And when I do that, I get 0. So what does it tell me? It's a factor. So I know that this is going to break down to x plus 3 times something else. So to tell me what that something else is going to be, I'm going to use synthetic division. And this is what I get when I use synthetic division. I get 1 and negative 4 are coefficients of x squared minus 4. So I know that my function is going to be x squared minus 4 times what I divided by, which is x plus 3. And I know that x squared minus 4, I can go ahead and factor to it, x plus 2 times x minus 2. And so now I know my zeros are negative 2, positive 2, and negative 3. Okay, now this one I definitely can't factor like it is. So first we check to see, is x plus 2 one of my factors? And I do that by checking to see if f of negative 2 is 0. And it is. So what does that tell me? Well, what it tells me so far is that if I go ahead and I divide this function by the 0 of x plus 2, then I am going to get a remainder of 0. So and I do. Okay, so what it tells me now is that I have 9x to the third power minus 36x squared minus x plus 4 is the remaining factor after I go ahead and split it up into those two. So now I can either see if I can factor that cubic part of the polynomial, or if I can go ahead and look for further zeros. In this case, I can go ahead and factor it by splitting, so I'm going to do that. Okay, and here's what I get. I get that the entire polynomial can factor to this, and so my zeros are negative 1/3, positive 1/3, positive 4, and negative 2. So what's the usefulness of this theorem? So this theorem helps us to be able to, 1, test to see if a linear factor is a 0, and then allows us to go ahead and factor completely any factorial polynomial that we may not have a technique that would work. Okay, so next we're going to go over the rational root theorem. So what we know about polynomials is that the degree tells us how many the maximum number of real zeros is. Okay, so we know that real zeros can be what we call rational or irrational. Okay, so irrational numbers are numbers like square root of 2, but a rational number is any number that can be written as a fraction. Rational zeros are those that can be written in the form of A over B. Okay, so what the rational root theorem, or zero theorem is, and I do call this the root theorem, rational root theorem, okay, can be used to determine if all possible rational zeros of a polynomial function. Okay, now this one, it is really, really useful, I promise. But sometimes it feels like futility. Okay, so, what it says is that whenever you have a polynomial, if there is going to be a rational root, it has to come from a specific set of numbers. That specific set of numbers is the positive and negative factors of the constants over the positive and negative of the leading coefficient factors. Okay, now it doesn't mean that they definitely are going to be zeros, but it says that if there is going to be a rational zero, it has to come from this list. And now remember, it's combination, so let's go ahead and look at how this works. Okay, so P in this one is 16. So what are my factors of 16? Well, 1 goes into it. It's even, so it's divisible by 2. 4 goes into it. 8 goes into it, and 16. Okay, now we go back to our constant. Leading coefficient. And we want factors of 3, so that would be 1 and 3. Now the entire list, it's not just that. It's a combination of those numerators with those denominators. So I have 1 over 1, which is 1, 1 over 3, and those are all positives and negatives. I have 2 over 1, 2 over 3, 4 over 1, 4 over 3, 8 over 1, 8 over 3, 16 over 1, and 16 over 3. Quite a list. So what this is saying is I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 possible rational zeros. Okay, so now we're going to go ahead and we're going to use it. So if I wanted to go ahead and I wanted to see if I could go ahead and find the solutions to this. First thing I'm going to do is I'm going to come up with, the first thing I'm going to do is I'm going to see if it factors. And guess what? It doesn't. So if it doesn't factor, and I'm looking to see if I can figure out at least one linear factor. So I'm going to do that by going ahead and doing my P's and Q's. So factors of 8 over factors of 1. So that makes my list a lot easier when my leading coefficient is 1 because I only have to test these 8 numbers. Okay, but if I can find 1, I think I would be pretty good. Okay, so I could use synthetic substitution, which means I'm going to go ahead and do f of that and see, do I get a 0? I could also use long division, but it doesn't matter how you do it. So I'm going to go ahead and I'm going to try 1. So I know I get 1 cubed plus 3 times 1 squared minus 6 times 1 minus 8. And then I go ahead and I do my math because right now I do not know if it actually equals 0. So 1 cubed is 1 plus 3 minus 6 minus 8, not 0. I don't even care what it's equal to. So I'm going to try negative 1. Negative 1 cubed. So that's going to give me negative 1 plus 3 plus 6. Negative 1 plus 3 is 2. 2 plus 6 is 8. 8 minus 8 is 0. Lo and behold, guess what I found? I found a 0. Okay, what does that tell me? That means if I go ahead and I do synthetic division, because I know that x plus 1 is a linear factor because it has a 0 of negative 1. So if I go ahead and I do synthetic division, I get this. So I have x squared plus 2x minus 8 times x plus 1 so far is what I know about my function. Okay, and now I'm going to see, is this factorable? If it's factorable, then I know all my zeros, and it is. So I get that my zeros are negative 4, 2, and negative 1. Fundamental theorem of algebra tells me I'm going to have 3 zeros. I found 3 zeros. I have solved it. Okay, let's do a couple more for practice. Remember on this, I'm trying to avoid factoring. I know I might be able to factor some of these. Okay, so first my P's and Q's. Okay, so I'm going to go ahead and I'm going to test 1. So if I go ahead and I test 1, my question is, does it come out to be a 0? So if I test 1, I get 1 cubed minus 2, which is negative 1. Negative 1 minus 18 plus 36, not equal to 0. So now I'm going to try 2. Well, 2 gives me 8 minus 8 minus 36 plus 36, which is 0. So that means if I go ahead and I do synthetic division using 2, I'll get a remainder of 0. So now I have x squared minus 18 times x minus 2 is my factored form. And now x squared minus 18, although I cannot factor it, I can't go ahead and use what I know about solving quadratics. So I know that to solve a quadratic, I could use the square root method. So I have x squared minus 18 equals 0, which gives me x squared is 18, which gives me x is plus or minus 3 square root of 2. So what I've done is I found irrational zeros as well. So I have 3 square root of 2, negative 3 square root of 2, and the first one I found, 2, are my factors of this polynomial. Doing number 6, if I go ahead and do the same thing, so my P's and Q's, I get, so those are all factors of 60, and possible factors of the denominator are just plus and minus 1. Okay, so now I'm going to test. Let's So I'm going to try 1 first because I like to start there. And it doesn't make a 0. So now I could test -1, but that doesn't work either. So now I'm going to go up. I'm not going to try the big numbers yet. Okay, so I'm trying +2. So I get, and neither does -2. So the hunt goes on. And finally, we get a bingo at 4. Okay, so what does that mean? What it means is I know one of my zeros is 4, and I use synthetic division next. Okay, when I use synthetic division, I get that f of x is x squared plus 5x, x cubed plus 5x squared minus 3x minus 15 times x minus 4. And because the math gods are being very nice, instead of having to do that again, which I could do, I have a factorable factor. So I'm going to split it up in half, take out x squared, and then take out a -3. So I get x squared minus 3 times x plus 5 times x minus 4. Remember, my goal is to find all the zeros. So even though this one is not factorable, I can use my square root method to get plus or minus the square root of 3. So I have x is square root of 3, negative square root of 3, -5, and positive 4. And fundamental theorem of algebra says I should have 4 roots, and I do. And that's it.